If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started.
All right, so we begin with hyperparameter tuning, and for this purpose, we've chosen a notorious model, which is a random forest. I'll tell you why it's notorious. As usual, I'm going to explain every single line of code to you, and I'm going to be giving you some very useful tips, some most common mistakes that people make when they do hyperparameter tuning, and as a result of that, they end up wasting a lot of time without getting anything productive out of it. So stay along and make sure you watch this video completely. There's a lot of learning coming your way. We begin by importing the basic libraries like NumPy, Pandas, and we are going to make our dataset using scikit-learn datasets module. This will be needing a class called make classification. So we are not taking the real data. We are creating a data just to demonstrate the idea of hyperparameter tuning to you. Then we are also calling the train test split. We are going to look at two popular approaches to hyperparameter tuning, the basic approaches, grid search and randomized search. And we are, of course, using the random forest classifier. Finally, we would want to evaluate our model as well. And we would also want to see how long do these approaches take? Because in the theory video, we discussed that randomized search is faster compared to grid search. How much fast it is, let's get an idea about it. So let's execute the first line of code, and all these necessary libraries have been imported. Now we begin by generating our dataset using this class called make classification. We are creating 10,000 rows, and samples is the number of rows, and features is the number of columns. So this dataset would have 5 features, and informative is equal to 5. So informative basically means that these features are going to be meaningful features for us. And redundant is equal to 0 means that we are not using redundant or correlated features, and we are using a random state just to ensure that our data, our results are repeatable and reproducible. Because this is a random data generation, we don't want to be changing the data set every time. So I'll just execute this. It generates the data in the form of X and Y. X would be the independent feature space, and Y is the target column. And now we are calling the train test split, where we are further dividing the data into 2 parts, train and test. And again, we need to use a random state for repeatability and reproducibility. If you are a practitioner of machine learning, you must be very familiar with these basics, but it's just that it's my responsibility to kind of iterate it again. Now let's use the default model. So let's not do grid search or randomized search to begin with. Let's try with the default random forest classifier. Now, if you go back to scikit-learn and check the documentation, every model comes with a set of hyperparameter values which are already present. We are going with those default values as of now. And calling the time library, we are calling the time method out of it, where we are capturing the start time. After we train the model using the train set, we are capturing the end time. And finally, the time taken to execute this would be the difference between the end time and the start time. This is just a simple string formatting where we display some kind of text along with any expression or specific variable references in 4 decimal places is how we are looking at it. Let me run this and see what happens. So this should be really fast. It says it took only 1.78 seconds. And let's see what's the output. First important tip, whenever you look at a model performance, don't just look at the train performance or test performance. We always need to compare them. I've seen a lot of codes where people just publish the test performance without showing the train performance. Well, you could seriously be facing a problem known as overfitting in those cases. You want to be careful. You look at train and test both, and then you'll be able to comment whether your results are stable and reliable or not. So let's just run this and see what happens. We are predicting using the train set, we are predicting using the test set, and we are generating the classification report for train as well as test. Let's see what happens. As you can see, our model seems to be perfect as far as training set is concerned because all the values are 1, which means 100%. So your model is great, looks like. But it doesn't necessarily echo the same performance in case of test because the performance came down somewhat. From 100%, we came to 93%, let's say for recall. And at other places as well, we have some dip in the performance on test. This is a moderate case of overfitting is what we are saying because we are not able to sustain what we got in our training set. Before we go to grid search, it's important to have a look at the common hyperparameters. So I've given the definitions of these hyperparameters. Please note these are model specific. Not for every model you have the same hyperparameters. These would vary depending on the choice of the model. Some of the models would have maybe 1 or 2 hyperparameters. Models like random forest could have 20 plus hyperparameters. You may use the common ones. So we are taking max depth, min sample leaf, min sample split, n estimators, and max features. Why it is important to know the hyperparameters is because a lot of times people end up giving unusual values to these hyperparameters and weird combinations of hyperparameters. I'll clarify that as I progress. And that's almost certain. Even before you hit or run the code, it's clear that you're not going to get anything. And I've seen people wasting hours of time not getting anything productive out of the model due to poor understanding of these hyperparameters. So I'll tell you what exactly I mean. Let's say for grid search, we actually have to define our grid, as in the hyperparameter space, using the dictionary structure. So we are creating param grid, which is a dictionary. These are the actual hyperparameter names. Please note, these names are exactly supposed to be the way they are used in the model. You can't give your own names here. This is something that you would know from the model documentation. So this max depth, you can't change it to something else. You can't write it as maximum depth. It doesn't work because this is going to refer to what your model understands. So let's say we've given 3 values, 3, 5, 7 for max depth. Min sample leaf, we have taken values like 10, 50, 100. Min sample split, we have taken values like 30, 150, and 300. Convention in case of random forest decision tree is that we take min sample split 3 times that of min sample leaf. Then we have taken n estimators. Now here is the important piece. I have seen so many cases where people will take values of min sample leaf as 1, 2, 3, 4. This is a big mistake. If you take these values so low, probably you've not understood the meaning of this hyperparameter. Let's see what it means. The minimum number of samples required to be at a leaf node. A higher value can prevent the tree from splitting nodes that have too few samples. If you take a higher value, it will create a controlled tree. If you take a much smaller or the smallest possible value, which is something like 1, it means you've expanded each tree to the last leg. Most likely you're going to get an overfit if you're doing that. So don't take values which are too low. Now, what is too low? What is too high? Also depends on the size of data. But if you take values like 1, 2, 3, on any data set, it's like you're expanding the tree to the last leg. So that's not the right choice, first of all. Second is, I've seen people taking pretty high values for n estimators. People would generally take values like 100, 200, 300. Please understand what it means. It means the number of trees in the forest. If you're creating 500 trees, 300 trees, obviously your system is going to get stuck. So the first common mistake is not understanding the hyperparameters and randomly taking values. Taking too low values where you're supposed to take relatively high values, taking too high values where you may want to be a little cautious to begin with. So we've defined our hyperparameter space here, and we are calling the random forest classifier with a random state again. We're calling it RF grid. Then we are calling the grid search, to which we pass this RF grid, this random forest model, which is going to get used for grid search. The param grid that we defined above, cross-validation as 5. Now, if you don't know what is cross-validation, you may refer to a video on cross-validation that we've already posted. And then, second important tip. I have seen people rarely use this option here. People would not often write what they're scoring on. Now, please understand, if you're solving a classification problem, you should also be familiar with the classification metrics. Not every problem is about delivering the best accuracy. Especially in cases when your data is imbalanced, you may not want to look at accuracy. So in this case, just to demonstrate, we've used a different scoring metric, which is recall. Once again, if you're not clear on which metric to use, I'll provide you a reference link. You can always refer to it. So you can customize this. If you don't do this, by default, the model is going to get optimized for accuracy. So I've seen so many times people are chasing recall or F1 score, but they're tuning for accuracy. That's again a problem, right? Another quick tip is, if you're running random forest and you have a relatively advanced configuration on your machine, you have multiple cores in your processor, you can use n jobs is equal to -1 as an additional parameter here. This ensures that you'll be using all the cores of your processor. So it'll make things somewhat faster for you. Once again, for random forest, we are capturing the start time, then we are fitting the grid, and then we are capturing the end time. Now, how many combinations is this going to run? So we have taken 3 values for max depth, 3 values for min sample leaf, 3 values for min sample split, 3 values for estimators, and 2 values for max features. If you know counting, it is 3 into 3 into 3 into 3. 4 times 3, that is 81, multiplied by 2, that is 162 unique combinations. So it's going to run 162 total possible combinations, and then it's going to give us the best possible combination as the response. Let me run this, and while it runs, I have something else to explain to you, which is the third most important thing that anybody should know while tuning a random forest model. So it's going to take time. Let me explain this to you.